Hi, my name is Emma Lotus, and today I'm going to tell you a tale of two plutons. It's about the compositional control on weathering, erosion, and landscape morphology. The story begins in Santa Gracia Preserve in central Chile, where my co-author Dirk Scherler and I noticed a landscape that had two different morphologies. One is lighter colored and has a higher drainage density, and the other is darker colored and has a lower drainage density. These two areas are underlain by two different granitoid plutons. One is a monzogranite and the other is a granodiorite. So you can see in this geological map that the outline of the monzogranite is almost the same as the outline of this area that's lighter colored and has a higher drainage density. So this is interesting, and we do know that lithology can impact landscape morphology. But here we have two very similar lithologies that have different drainage densities. And so we're wondering, what are the causal mechanisms? Differences in drainage density can be due to climate, infiltration, sediment size, or vegetation cover, for example. But here the climate is the same. So we're going to look into some of the other factors and see if they have an influence. So in this talk, I'm going to confirm our field observations and attempt to understand the causal mechanisms by quantifying the drainage density, the grain size, the vegetation cover, and the bedrock geochemistry, which can tell us something about the weatherability and the erosion rates of these two rock types. Our hypothesis so far is that drainage density differences are primarily influenced by infiltration by rainwater and also by differences in vegetation cover, which cause interception of that rainwater. So first, the drainage density we quantified using GeoNet, which is a method that doesn't artificially set the upstream area threshold, which makes it a bit less biased. So we found that the monzogranite does indeed have a higher drainage density and also almost twice as the amount of channel heads per area. So this confirms what we observed in the field. Then we quantified the grain size. And we did this in the field by conducting grain size counts in transects along the hill slopes in the two rock types and counting the grain size on the surface at around every meter. And we found that the grain size is larger in the channels in the monzogranite, but larger on the hill slopes for the granodiorite. Then we quantified the vegetation cover, and we also did this in the field doing walking field surveys where we observed the density of vegetation along transects along hill slopes in both rock types. And there we found that the granodiorite has almost twice as dense vegetation cover as the monzogranite. We also quantified the vegetation cover using remote sensing and LiDAR. And there on the left, there's a Landsat image where the darker colors indicate more shrubs. And you can see that it's much darker in the granodiorite, which indicates more shrubs there. And then on the right-hand side, there's a LiDAR image where we took the original returns and we subtracted bare earth returns. So what we have is elevation of what should be the vegetation above the bare earth. And you can see that in the granodiorite, there's more darker areas, which indicate higher vegetation cover. So all of these methods agree that there's more vegetation in the granodiorite. So finally, the bedrock geochemistry. We took 18 samples for X-ray fluorescence and also 16 samples for 10 beryllium erosion rates. And we found that the granodiorite has a more weatherable composition, and that's because of higher amounts of sodium, calcium, and iron. And it also has more plant essential nutrients, including phosphorus and magnesium. So because of this, we think that the granodiorite's composition is more weatherable, and also that maybe the landscape is phosphorus limited, and that's why there's more plants in the granodiorite, because there is more phosphorus there. So in terms of erosion rates, we found that the erosion rates are relatively similar between the two sites, and they're around 10 meters per million years. So to conclude, this is preliminary data, it's an ongoing project, but so far we have found that in the monzogranite there's higher drainage density, larger grains in the stream channels, less weatherable composition, less plant nutrients, and less plants, and we have the opposite going on in the granodiorite. So going back to our hypothesis, are drainage density differences influenced by infiltration and interception by plants? And we think that it could be true. So the granodiorite seems to have a composition that's more prone to mineral dissolution and infiltration. That can lower surface runoff and drainage density and also promote plant growth. And we see more plants there. those plants can intercept more water, retain more water, create less surface runoff, and also a higher threshold for fluvial incision, which lowers the drainage density. So it all works together. In terms of the grain size, we're not sure yet, but it's possible that the difference in grain size distributions between hill slopes and streams in the two rock types has to do with difference in dominance of hill slope and fluvial processes. So we're going to look more into that going forward and also conduct more experiments and make more measurements. So stay tuned, and if you have any questions, comments, suggestions for this project, anything, please email me. My email is at the bottom of each slide on the lower right-hand corner. Thank you for listening.